Okay, well, thank you very much. It's a great privilege to be here and to talk to you about this very important topic, the whether M dwarf has an atmosphere. So this subject was covered quite a bit, and in fact, Jonathan really captured the actual theoretical challenge. Do do planets around M dwarf survive the harsh environment? It's far from clear. And we love indoor because they're small, everything is easier around them. But it's a very important questions that, in fact, only JWST can answer for quite a while. So the background of this is also that not just rocky planet could be habitable. And Niku presented this case of Aishan's world. So we should be, of course, interested about temperate rocky planet, but there's also interesting things going on the right of the Radius Valley. And in fact, that bimodal distribution captures a lot of physics, atmospheric escape processes, planet formation pathways, and of course, the big question is, do planets on the left side of the super Earths, and in particular the one in the middle, do they have an atmosphere? So, and related to this question is the notion that do water world exist? There's many candidates of those. So by water world, we mean a planet in which a significant fraction of its bulk mass is made out of water. And those are extremely interesting from the questions of habitability, and the temperate version of those are in particularly very interesting. And I'm going to talk about one in a minute, which is LHS 1140. And so this is on the right here, very nice work by Karen and Pierre, showing two examples of two planets on the left side of the Radius Valley, showing evidence of a significant water mass fraction. So, I mean, these things exist, right, in our solar system. They are called Europa and Enceladus, and so water world should exist, and JWST should be able to identify the example of such worlds, and of course, atmosphere will be key to this. So we have two wonderful techniques to do it: transition spectroscopy and also eclipse photometry. We've seen both results, and this equation just captured a challenge to do it on solar type stars, and that's why we love M dwarf. The R square factor boosts the signal by a factor of 100. So this is what we call the M dwarf opportunity. Okay, so and in fact, JWST has a sensitivity. Before launch, people were wondering, can JWST reach the sensitivity of a few tens of ppm? Well, it's now demonstrated. This is one data set from NIRISS, and you can use that with NIRSpec. One can reach 5 ppm and less in about an hour of observing time, and that's what you need to really characterize very thin atmosphere that usually will take quite a lot of time. Okay, so in terms of target, there aren't that many. Yes, we have 5,000 exoplanets, but if you look at a subsets of planets with effective equivalent temperature less than 300 Kelvin, because above 250, if you have a significant water mass fractions, then the greenhouse effect will actually rapidly warm up the planet to in a state where water becomes supercritical. So you can't really describe this planet as being habitable. So if you take a cut at 300K, and Niku made that point, these are the targets. KT18b, the TRAPPIST-1 planets, and LHS 1140b, and so those actually really capture the Radius Valley. So K218 on the right side, the TRAPPIST-1 planets on the left side, and LHS 1140 that I will talk about is right in the middle of the Radius Valley, and they all have exquisitely good mass and radius constraint now. Okay, so the TRAPPIST-1 is obviously key to this. D, E, F, G are the likely planets where we could have habitable conditions. So I'm going to go very quickly what we've learned so far on those planets. I'm glad I put most likely airless, because Michael just showed this morning that TRAPPIST-1b may have an atmosphere, but the current MIRI observations suggest a very hot day side. The same story, this is going to come back. My next slide is about TRAPPIST-1c. Yeah, so there you go. TRAPPIST-1c, which it's more ambiguous. There may be a thin atmosphere. The data may be compatible with a thin CO2-rich atmosphere, and it's just emphasized the power of eclipse photometry with MIRI, which is a very simple experiment. aperture photometry is so simple to do and a very powerful technique, and really warrants a lot more time for to probe for atmosphere around the TRAPPIST-1 planet. Now, for transmission spectroscopy, the first spectra came from NIRISS on TRAPPIST-1b, and this was really a story of stellar activity. We see lots of variations in the white light curves. Sorry, let me bring this. I will not. Okay, so on the left you see white light curves over 2 visits, and that was actually key to observe these things twice. And so we were able to show that the spectrum is variable. On the right, you see evidence of the so-called transit light source effect, the fact that you have unocculted spot or faculae. If your planet happens to go a chord that does not have the same spot and faculae distribution, then this will bias your spectrum. And that's a very insidious effect, because that may generate features like a slope or even a water feature. You may think you have an atmosphere, but in fact, it may not be. So it's an issue not only for TRAPPIST-1, but also any atmospheric characteristics, including giant planets, how to really take into account stellar activity. Okay, and another thing that I come across, which is obvious with Webb data now, but also from high-resolution spectroscopy, is that unlike the beautiful spectra we saw for one drug, where we have a perfect match between data and the model, stellar atmospheric model really are not a good match to data. And that's a big deal, because we're now using stellar atmospheric model to correct stellar activity in transmission spectroscopy. And that's a major problem that we need to solve. And then there's in the short terms, we cannot wait for theoreticians to come up with better model. We're going to have to use empirical data. Okay, so flares. Flares are extremely frequent on TRAPPIST-1. We now have good statistics. They come to about every 6-7 hours. So essentially, half of the data you take have a flare. It's an example here on our GTO program, TRAPPIST-1F. We were less lucky than Nicole here. 3 out of our 5 transit has this kind of huge flares, and it's actually quite a challenge to correct for them. They show black body features, but we have yet to understand the property of these flares to correct from them in transit spectroscopy. Hopefully, and that was we never planned for this, but we turned out to have extremely good throughput, both with NIRSpec and NIRISS at H alpha, 0.65 micron. And in fact, that allows us to actually monitor. It's a good beacon of flare. Okay, but the TRAPPIST-1 is sometimes quiet. And as part of our reconnaissance program, we also took a look at TRAPPIST-1G. This is a paper by Björn Benneke, which is currently under review. And this is a case where TRAPPIST-1 was very quiet. In this spectrum, there's almost no evidence of transit light source effect. And we're reaching extremely good sensitivity at the level of about 30 and 50 ppms. And we can exclude many cloudless models. And it's a busy plot here, but there's one model here includes a thick CO2 atmosphere that would be compatible with liquid water on the surface. And the CO2 feature is about 50 ppm. So in 2 visits, we are already there. So it just shows the potential and the power of transit spectroscopy to characterize the planet of the TRAPPIST-1 system. But of course, one will need to correct for stellar activity in general. Okay, now what is the next step for TRAPPIST-1? Of course, a lot more MIRI eclipses. We've seen the power of that, and there will be a program in cycle 3, and we can suspect that a large fraction of that time will be dedicated to do eclipse spectroscopy, eclipse photometry for the TRAPPIST-1 planets. But we really need to understand the stellar activity. And one way to do it is basically to monitor TRAPPIST-1 over one full rotation, 3.2 days, to better understand the flares and the stellar heterogeneity. It's actually fundamental. It's not only for TRAPPIST-1, it's in general to understand how one can correct for stellar activity. And also another strategy is to, we have so many transits, and if B turns out to be airless, well, you can actually shoot for multi-transit. When you have B with coupled with another transit, and you can use B as a sort of a beacon for transit light source effect. So that way you can, make corrections of stellar activity. Okay, now let me move on to another interesting target, which is LHS 1140b, which we recently revised its mass. We basically reanalyzed the existing radial velocity data, the exquisite data from the espresso spectrograph, and we devised a new algorithm that actually improved the salinity by almost a factor of 2. And that led to a new mass measurement, slightly less, a different mass, and also a new radius, suggesting that LHS 1140b does not lie on the Earth-like track. It looks like it has a, well, in fact, there's three possibilities. It's either a mini Neptunes, or it has a singular fractions of water, or it's a, a strange pure rock planet. So we did internal structural models of this thing, and in fact, we have abundance measurements from high-resolution spectroscopy with NIRPs of the refractory elements, magnesium, silicon, and iron. And all models converge to the same thing, that whatever you assume for the refractory abundances, this planet, the best model is that a water mass fraction of about 14% and a core mass fraction of about 20%. Just for reference, the Earth is about 30%. So the core mass fraction refers to the fractions, the bulk mass in iron in the core. Now, just to test the hypothesis that this thing could be a coreless planet, so if you force the water mass fraction to be 0, then the model converges to a very low core mass fractions of about, less than maybe 8%. But with abundance ratio of iron to magnesium that are way off compared to observation. So it's very unlikely that this planet is actually a coreless planet. And in fact, it's supported by synthesis model of exoplanets, where the bulk of planets are formed with a core mass fractions of similar to Earth, 30%, and this is where LHS 1140b lies. It's within 95% of most planets that that the nature can form. Okay, so we're left with only two possibilities. Is it a mini Neptune or a water well? And this is where translation spectroscopy comes in. We can actually constrain the two. And I'm going to show it later, but we did the detailed GCM models of the water well case. And in that case, and it's a paradox. It's a water well, but we don't see any water because there's a cold trap. And the only feature that we see is CO2 beyond 2 micron. And if you look at the scale here, these are the amplitudes are about 15, 20 ppm. So this will take quite a lot of time to do this if that's the case. So that plot was a justification to actually try to salvage the 2 remaining visits in cycle 2 for a director of the differentiated program that we got. And we got a first spectrum with NIRIS on December 1st, beautiful spectrum. And we didn't realize, so we got a second visit just on the 26th, and we realized a few days before that we would have a Christmas gift, a double transit. So we got a spectrum of C and in bonus for this. So I'm going to show you for the first time the actual spectrum. But first the radius, and just to capture, when we say JWST is powerful, one single visit with nearest JWST, beats the radius of any observation that was done before with TESS, HST, Spitzer, and this is, and we're improving the radius again at sub % now, which is, LHS 1140b is joining the TRAPPIST-1 planet in terms of quality of radius measurement. So here's the spectrum. It's flat. There's still some wiggles in there, and the dotted line is the best GCM model of a mini Neptune. So this thing doesn't look like a mini Neptune. So the best hypothesis that we have right now for this planet, that this is a water well. Now the question is, does it have an atmosphere? So this is the GCM models made by Martin Tourvet, and that was published in our paper by Charles Cadieux. And of 2 hypotheses, this is one that has 400 ppm of CO2, and the solid portion here shows the regions where you have liquid water. So there may be liquid water at the substellar point of that planet. And of course, if you add more CO2, this thing gets bigger. But the thing is that no matter how much pressure CO2 you put in there, the CO2 feature at 4 microns remains the same. It's about 15 ppm. So The next big step for this is, of course, eclipse photometry. So you can make a back of the envelope calculation to predict that the eclipse depth should be about 73 ppms, and that would take about 8 visits. Now, there's one very important thing about this planet is that its visibility is very limited. There's only 4 visits a year, 4 transits and 4 eclipses. So it will take 2 years to acquire that data. So we need to start now. Which is my last slide. This is a proposal to look at rocky planets with MIRI. There is a recommendation to use the 500 hours to look at to do eclipse photometry of rocky planet, which I fully subscribe to. And don't take these numbers to the digits, but these are back of the end of the calculation to make the point that we're going to need the bulk of the 500 hours just to look at the TRAPPIST-1 planet. But I would like to make a plea that we need to do also transmission spectroscopy, because to detect the CO2 feature with near spec and the most likely, the most winning configuration would be to alternate between G35 and 395, would take 3 years worth of data. So we don't want to let this kind of program to attack weather. We should do it now. Okay, so I'm going to end on this. So, and my summary is that TRAPPIST-1, LHS 1140 and K218 are keystone system to assess habitability, and that I think should justify deep dive studies. Stellar activity is a serious, but I would say a tractable problem that basically that requires in-depth stellar activity characterization of the TRAPPIST-1 planet, and the sooner the better we do it. And well, I hope I've convinced you that LHS 1140b is probably one of the best water well candidates we have. And that this one probably one of the best targets from which we can infer liquid water on its surface. And the next step is both MIRI eclipse photometry and deep transmission spectroscopy with near spec. Thank you very much.